Welcome to Soil Resources Inventory NREM 221. We will be posting all of your content on Canvas. You'll also find the syllabus there, which outlines a lot of the course rules, objectives, what book to get, where to get the book, when we're going to meet for lab, how grading works. We're going to introduce the land use project at some point this semester. That'll be mostly in lab. And of course, you'll see a course calendar with each week's topics, suggested reading, and of course, when we will host exams. So first, go read the syllabus, and then we'll talk about me, myself, and I, and a little bit about you. A little bit about me. My name is Dr. Haft. I go by Dr. H. I grew up in California on a beef cattle ranch. I then did my first 2 degrees at Cal Poly San Luis Obispo in pre-veterinary animal science and soil science, and then I got my PhD at the University of Kentucky in soil science. And that brought me here where I met my partner, and we have a very large family, and it's wonderful. I love climbing and working out, and this is a picture on the bottom left of me holding my grandmother, who is my hero. This is some of my family. We had a very large rabbit named Moose, who has since passed on, unfortunately, but I will forever keep his photo in this presentation because he's marvelous and hilarious. And then there's a spoiled rotten hound dog here. Her name is Petunia. She's a stealer of socks and a lover of cuddles and just my baby girl. So now what I'd like you to do is tell me a little bit about you, and I will have a discussion board set up where you will verify that you read the syllabus and then tell me a little bit about yourself. Introduce yourself to the class. So we're going to start with chapter 1, just introducing you to the general idea of soils and what they are. So today's learning objectives are to describe the 5 key functions of soils and ecosystems, to characterize the way in which soils interact with the lithosphere, hydrosphere, biosphere, and atmosphere, and explain how and why O, A, E, B, and C horizons differ from one another within a soil. We're going to compare and contrast topsoil and subsoil, and we're going to characterize the 4 primary constituents of soils: minerals, organic matter, water, and air. We're going to diagram the ways soil provides nutrients to growing plant roots, and we're going to list 5 ways that human activity can diminish soil quality. I'm going to post a link to a video in the page created for this part of the course. It won't show up if I click it now, so just FYI, make sure you watch that video. It's a great introduction. First, we're going to define soil and why soils are important. 95% of all food and fiber comes from the soil. 99.9% of all fresh water passes through soil, and most of the world's antibiotics were isolated from organisms that live in the soil. By definition, soil is unconsolidated mineral and organic material that serves as a natural medium for the growth of plants, provides consistent and pure water supplies, recycles nutrients and wastes, modifies the atmosphere, provides habitat for numerous soil organisms, and is a basic engineering medium. As a plant growth medium, soil provides support, nutrients, water, gas movement, and growth-enhancing compounds. There are quite a number of required nutrients for things to grow healthy and strong in soil, and we're going to talk later on in this course about how they all play a role. The regulation of water is a huge part of soil's ecosystem purposes. So soil is basically a valve that regulates runoff and infiltration, and it's also acting as a water filter. Think of the pedosphere as a giant sponge that water trickles through to filter out all the bad things before it gets into groundwater, where we generally pump it out for our general uses, or where it seeps out into streams and lakes and rivers and other surface water reservoirs. It's a recycling system, okay? It takes basically dead things or decaying things, and little microbes degrade all of these things down back into their actual original elements. And those elements are then recycled through various forms. And so soil is the ultimate recycling system. Here you can see there's biogeochemical cycles involved in all of this that incorporate this carbon cycle, the nitrogen cycle, the sulfur cycle, the phosphorus cycle. The cycles go on, my friends, the cycles go on. It's a modifier of the atmosphere. We have increased human health issues, such as asthma when there's too much dust in the air. We can alter Earth's surface temperatures when there's too much soil in the air. In fact, there is a theory that that is how the dinosaurs died, that an impact at the Earth's surface caused giant dust plumes to block out the sun, killing all plant life, changing the Earth's surface temperature, making it too cold for anything to survive. And then, when all the food sources were gone, so were the dinosaurs. Sad panda. Gotta tell you, that must have been rough. Ha! Anyways, if you've ever been in a dust storm, you know that it also includes reduced visibility. And overall, soil modifies the atmosphere because it literally breathes. It's an ecosystem that takes in oxygen to feed the microorganisms the air they need to breathe. And then it exhales. There's the word I'm looking for. It exhales CO2 into the atmosphere. And so this is to be said of a lot of other gases as well that come in and out of the soil, almost like a giant dirty pair of lungs. It's a habitat, maybe billions of organisms in just one spoonful of soil. The microorganisms and macroorganisms that live in the soil consume things. They're predators, they're prey, they're producers, they're consumers, they're parasites. There's a whole ecosystem in there. It's so exciting. It's an incredible engineering medium, soil is. It's a place where we design roads and houses and buildings. And in order to do these things, we're going to have to understand things in terms such as bearing strength and compressibility and shear strength and shrink swell. These are all terms that come together to really understand how to use soil as an engineering medium, and we'll go through these terms as we progress through the class. Soil is organized, believe it or not. It's not in disarray. The major components of soil. There's about 47% mineral matter in the soil, about 3% organic matter, 17% air, 17% available water, and about 16% unavailable water. We design our taxonomic system of soils around looking at the soils for various features. And in order to do that, we basically dig a giant grave. I know it's a little maybe not lighthearted, but stay with me here. We dig 6 feet down, okay, and we look at the soil like a slice of cake taken out of the earth, okay, and that what it shows us in this vertical section are layers, like cake layers. There are different colors, there are different textures, they have different shapes. Lots of different things have occurred to create these really fun horizons. Here, as we look at a horizon, at the top of this soil profile, we have a dark, rich horizon, roughly parallel to the Earth's surface, and it's going to differ from the horizon below it, where it's much lighter because things have leached out of this lighter horizon and been accumulated down here in these lower horizons, which are also a different color and texture and lots of fun different things. Basically, horizons are layers of soil roughly parallel to the Earth's surface that will differ in properties from those above and below. We designate these soil horizons with capital letters to signify the major soil horizon characteristics. So for example, if we call something an O horizon, it's an organic surface layer. Generally speaking, we find organic surface layers in areas where Plants grow faster than they can decay because there's usually a lot of water, and it decreases the number of organisms that can break down the plant matter. And so we end up with these really, really thick accumulations of partially decaying plants. Generally speaking, this is going to be in a wetland area. Think peat bogs, that kind of thing. Also, we can find organic surface layers in forests where leaf litter accumulation is used to protect seedlings dropped by trees. An A-horizon is what we usually find at surfaces, which is a mineral horizon at the surface, or in the cases of forests or wetland areas, right below that O horizon. An E-horizon is an eluvial horizon, an exiting horizon. Things are exiting out of an eluvial horizon. E for exit, that means we're losing organic matter, we're losing clay, we're losing iron, and maybe even aluminum. The B horizons are subsurface horizons of clay or iron accumulation. These are illuvial horizons. Things are coming into them. I for into. The C horizons are relatively unweathered, unconsolidated material. This is the parent material horizon, and they're usually identified by massive structure. Hold on to that term, we'll come to it in future presentations. And finally, where we have consolidated bedrock, we have R horizons. Now, not every profile will have all of these horizons. We'll see examples where we have bits of some and others will be missing. During the basic soil building processes, we're going to have additions, redistributions, think illuviation and illuviation, where things are either exiting or coming into the horizon. We're going to have loss of materials from the profile through leaching and erosion. It's all of these processes that are the basic soil building blocks. So in this profile, for example, we have an O horizon at the surface, an A horizon right below that, an E horizon, an exiting horizon, an eluvial horizon that has dropped things into a series of maybe 3 or 4 B horizons, which are illuvial because they have things coming into them, illuvial for I, into. In the C horizon at the bottom, we have unconsolidated parent material, and then we have a consolidated layer of what appears to be digital marble, because I couldn't get a picture of rock. Topsoil and subsoil. So when we talk about topsoil, we're talking about the A horizon, the plow layer, the furrow slice, the top of this soil profile. This is where most plant roots grow. This is the most nutrient uptake. This is where all the money is. Folks, this is a very important horizon that we don't want to lose to erosion because it takes a very long time to get it back. In our subsoil B horizon, which has lower organic matter and is more highly structured, we have the importance, potentially, of water provision under drought stress in these horizons. Our subsoil generally provides water for deep tap roots when there's times of drought stress. Subsoil is very important. It's also a huge engineering medium that we have to understand for building things. We have an influence on soil quality, humans do, and soil quality is generally, literally, the quality, the usability, the value, the resource, the usability of the soil for various purposes, okay? And our influence has been maybe we degrade soil quality because of water erosion or salt accumulation from over-irrigating, from soil organic matter depletion from overcropping it, diminishing the soil fertility. Maybe chemical spills have contaminated it, and yet despite all of these, soil as an ecosystem can fight back. Soil resilience, however, does vary based on the soil type, its various features, and overall soil quality from how it's been managed previously. I wanted to highlight this text figure because it really shows pedosphere interactions. It shows how in the atmosphere, We see an interaction with soil air through gases like carbon dioxide, oxygen, and nitrogen. And in the biosphere, we see interactions between plants, animals, microbes, their products, and their remains with organic matter and biomass in the soil pedosphere. And in the hydrosphere, we see water dissolved substances interacting with soil water. And in the lithosphere, we see minerals and rocks, clays, and sediments interacting with individual soil particles. And the ways in which they do these things overall will affect the ecosystem. I wanted to also highlight the soil nutrient interactions with roots. The structural framework of soil, of primary minerals and organic matter, makes things slowly available. Over time, they break down to something called the colloidal fraction, which is the smallest type of soil particle. This structural framework of clay and humus slowly allows nutrients to become available. Where they're stuck on the adsorbed fraction, like post-it notes, to the surface of the individual soil particles, the colloidal surfaces, they become moderately available and then they start diffusing between the plant root and soil solution. And here's yet another kind of more blown up version of the end of that last figure where we have soil particle diffusing ions to a plant root.